We've defined a very simple and naive search algorithm that tries to find solutions to random 3-sat formulas. It doesn't even backtrack. It just cruises down a random branch of the search tree and either gets lucky and finds a solution or hits a contradiction and just gives up and says, you can always try running me again. So let's actually try to analyze how well this algorithm works on random formulas and try to compute the density at which it succeeds or fails. The hope is that even this very naive algorithm will succeed in finding a solution, at least some of the time, up to a certain density. It turns out that for random formulas like this, we can analyze this kind of algorithm using differential equations. I think this is really nice because in computer science, most of the mathematics is discrete mathematics. You know, strings of bits, graphs with nodes and edges, and so on. And techniques from continuous mathematics, using things like calculus and differential equations, are actually relatively rare in computer science, even though they happen all the time in other sciences, where we use continuum approximations to deal with whenever a system has a large population, a large number of atoms in physics, a large number of individuals of some species in biology, we say, well, let's call this a real continuous number instead of an integer. And then often we can use things like differential equations to track the population and so on. So it's kind of fun that this can work, at least in this case in computer science. So here's what we're going to do. We're going to track the number, or actually the density, of clauses of different lengths. Initially, all of our clauses have 3 variables in them, but remember that when we set a variable, then this clause here either disappears if we gave that variable the value it likes, or it gets shorter, demanding something from its remaining variables if we give this variable the value it doesn't like. So as the algorithm proceeds, there might be some 3-variable clauses that haven't really been touched yet. There'll be a bunch of 2-variable clauses which have gotten shorter. And then there might be some unit clauses, some 1-variable clauses that are loudly demanding a particular variable gets set a particular way. So we're going to use differential equations to track the population of clauses of different sizes. Now there's an important thing which will simplify our analysis. Remember that our search algorithm, if there are currently no unit clauses, it gives a random variable a random value. If there is a unit clause, or if there are multiple ones, it chooses one randomly, it gives that unit clause the value that it wants that variable to have. Now put yourself in the shoes of, say, a 3 clause sitting over here. You have a particular variable, and let's say that we've chosen to set that variable. Now, we're either setting it in what you might call a free step, where there are no unit clauses, so we just happen to choose this one and we flipped a coin. Or we're choosing it in a forced step because somewhere else in the formula there was a unit clause demanding that this variable take a certain value. But the whole formula is random anyway. So from your point of view, it's completely random. It's half and half whether the value that this variable is given is the one that you agree with or not, because the value that you wanted to have was chosen independently from the value that all the other clauses wanted to have. So that's handy because it means that the probability that the next step eliminates this clause or shortens it is 1/2, no matter which type of step the algorithm is doing. All right, let's invent some notation. Let's say that the number of clauses of length 3, those 3-sat clauses that are left over from the initial formula, is S3 times n. It's linear in n, so S3 is a real number. It's the density of those clauses. And let's say that currently, having satisfied some clauses and shortened others, we have S2 times n clauses of length 2. And let's also say that we have set a fraction t of all the variables. So t times n of our variables have been set, and 1 minus t times n have not yet been set. Well, we can now write down some differential equations that give us the average or the expected change in these densities over time. And again, if you've seen this type of differential equation in ecology or biology or physics, then it's quite familiar. But if you come from computer science, then, well, what I should really say is that there is a stochastic process that takes integer values, and that what we're computing here is the average change in these integer values, and then we're taking the limit as n goes to infinity, and then we're dividing by n to scale these to real numbers. But I'm happy to tell you that if you're interested in mathematical rigor, this all can be made rigorous by tracking the typical fluctuations in these integers and showing that they do, with high probability, hug the trajectory of this differential equation. Good. So, let's look at these differential equations. What is ds3 dt, the typical change in the density of three variable clauses? Well, it's a little bit like radioactive decay, right? If you have a bunch of plutonium atoms, then in each moment of time, each one of these has a certain probability of decaying and not being that isotope of plutonium anymore. And so the probability that the probability that we lose one of them is proportional to the number of them that we have. So the probability that a particular 3-sat clause is about to disappear is, well, each of these three variables could be the one which we choose to set next. Now, there are 1 minus t times n variables we haven't set yet. And so the probability that one of these three variables is the one the algorithm chooses to set is 3 divided by 1 minus t times n. We scale away that factor of n to make the differential equation, and we get 3 over 1 minus t. And that's the probability that a particular three variable clause disappears, either by getting satisfied and leaving, or by being shortened into a 2 variable clause. And so this differential equation gives us minus 3 over 1 minus t times s3. Okay, all right. So what about the other differential equation? What's the typical change in the density of 2 variable clauses? Well, this is roughly the same reasoning. First of all, a 2 variable clause has 2 chances of its variable being set next. So we have this term where they decay at a rate which is 2 over 1 minus t, the fraction of variables that haven't been set yet. But on top of that, half of these 3 variable clauses become 2 variable clauses when we set one of their variables. So we have this term 3/2 of the 3 variable clause density feeding into the 2 variable clauses. And so we have that 3/2 s3 on the top. What else do we need to get our differential equations off the ground? Initial conditions. Well, at time 0, s3 is alpha, because initially we have a random formula with alpha n clauses, all of which have 3 variables each. And initially, at t equals 0, s2 is 0. So we've defined these differential equations to track the density of 3 and 2 variable clauses. When we solve them, we get these formulas describing these curves. The density of 3 variable clauses is in blue, and you can see that it just decays, indeed down to 0. Every 3 variable clause at every step has a certain chance of just disappearing, either because, again, it gets satisfied or it gets shortened. Meanwhile, the density of 2 variable clauses at first rises as some of the 3 variable clauses get shorter and turn into 2 variable clauses, and then it decays as the algorithm continues to try to satisfy everybody, and hopefully it satisfies these 2 variable clauses as well, and they decay down to 0. You may have noticed that we haven't talked yet about what in some sense are the most important and urgent clauses, the unit clauses. Well, there's a reason for that. The number of 3 variable clauses and the number of 2 variable clauses is linear in n, linear in the size of the system, the number of variables. But if the number of unit clauses ever got to be linear in n, we would already be dead. Because suppose that one unit clause wants x17 to be true. Meanwhile, another unit clause wants the same variable x17 to be false. Well, now we're doomed. To be more precise, we would have to backtrack because we just cannot make both of these unit clauses happy. But remember, this particular algorithm just charges through and sets variables permanently. So at some point, it's going to satisfy one of these and make the other one very unhappy, and then we'll have a contradiction, and then it will say, oops, sorry, I failed to find a solution. In fact, there is a classic problem in probability theory called the birthday paradox. You may have heard it before. It asks, how many people do I need to get into a room before the chances are pretty good that 2 of them were born on the same day? And it turns out you don't need anywhere near 365 people. You only need about 27 or 28. In fact, if we have n variables, as soon as there are about square root of n unit clauses, it's pretty likely that 2 of them contradict each other. So the lesson of all this is that when we use differential equations, we're usually assuming that some variable is very large, so that rather than treating it as an integer, we can basically treat it as a real number. But if the number of one variable clauses gets very large, we're already dead. So our analysis is going to use a nice hybrid of continuous mathematics and discrete mathematics. We are going to think of the number of one variable clauses as an integer, which we're going to hope is actually 0 most of the time.